So we continue the exciting session of our summer school workshop, where we will now have another wonderful episode with Edward Farhi, a professor of physics from MIT, as well as a principal scientist at Google working on quantum computation, a world-class expert in the field and a wonderful person. Edward Farhi received his PhD from Harvard University. He was the director of the Center for Theoretical Physics at MIT from 2004 until 2016. Professor Farhi made important contributions to particle physics, general relativity, and astroparticle physics before turning to his current interest, quantum computation. He has kindly agreed to join us for this school, and he's going to give a great talk entitled Physics-Based Quantum Algorithms. With this, I want to invite Professor Ed Farhi to the stage. Edir, please come.
Thank you. Can you hear me okay?
Yeah.
Well, Nu, that was a great talk. Fantastic. I have to say, a hard act to
Thank
follow.
you.
But first, let me just say a word about myself. First of all, my grandparents were born in Izmir, and I have a Turkish name, although that was a long time ago. So my roots are in Turkey.
I see.
Yes, but I started in particle physics, and then about 25 years ago, I became interested in quantum information and quantum computing. And I shifted my interest, remaining at MIT. And then about 5 years ago, I became a full-time, I started working for Google. I do research for Google, but I still spend most of my time at MIT talking to researchers there. And I'm basically just doing research, although I am paid by Google. So that's who I am. Okay, now I'm supposed to share my screen, right?
Yeah.
You see my screen?
Yes.
It works, yes.
Okay, thank you. Okay. Let me close everything, and then I'll go to full screen, and hopefully we can begin. File. No, I want to go here. View. Slideshow. Okay, are we good now? Thank you. Okay, thank you. So, well, why did it advance? Okay, let me go back. So anyway, my title of my talk is Physics-Based Quantum Algorithms. And again, I already said who I am. My affiliations are Google and MIT. So basically, though, this is a talk about quantum algorithms, which means that I'm really not going to be talking about platforms. I'm always going to sort of in the back of my mind imagine that I have a perfectly functioning quantum computer. And the question is, what can we do with that device? Not how do you build it? Nothing, just, what do you do with a perfectly functioning device? Okay, so, so let me review a few things about quantum computing. I know that you had some kind of school beforehand, but hopefully we know a little bit, but I'll help you out. First of all, that equation in the red box, ID by dt on psi is ht psi t, that's what I call the Schrodinger equation. There's never a violation of that ever seen. That's just the truth in a scientific sense. The Schrodinger equation, if I give you the Hamiltonian, you have time evolution. But it implies that if the Hamiltonian is Hermitian, that the wave function at a late time is given by a unitary transformation acting on the wave function at an early time. So in that sense, you can think of quantum computing as an application of a sequence of unitary transformations. And that's what we call the gate model of quantum computing, where you act with a unitary, another unitary, another unitary. For example, the Shor factoring algorithm is written like that. But I want to take a different approach, and I would like to base the quantum algorithm on the Hamiltonian itself, and do it by continuous time evolution. So then I say, okay, that's so general. We're just going to evolve with some Hamiltonian. What does that mean? So we need to have some vision for what a quantum algorithm is. Well, the first thing you need to have is a problem to solve. We're just not going to, vaguely search the internet or something with our quantum computer. We want to have a specific computational task that we want to solve. And then what we're going to do in this physics-based approach is we're going to design a Hamiltonian, which is helping us solve this problem. Then what we're going to do is pick an initial state. Then we're going to pick a runtime. And then we're going to evolve with the Schrodinger equation because there's no alternative. You can only evolve with the Schrodinger equation. And here I'm assuming that we have perfectly good unitary time evolution. There's no noise. I'm just ignoring noise and I'm just focusing on Hamiltonian time evolution. So if you evolve for time capital T, then you have a new wave function at time capital T. And we then have to measure some operator. Then we're going to measure something. And we want the result of the measurement to encode the solution to the problem. So this is my vision in a way of quantum computing in the Hamiltonian domain. But you need all these things for it to make sense. And the algorithm designer has to design all these things, the Hamiltonian, the initial state, the runtime, the evolution according to the Schrodinger equation. That's just what the quantum computer does. It has no choice. And the choice of the measurement outcome. But then the question is, how does the runtime scale with the problem size? Because you might come up with an algorithm where you run forever and then you get the solution to your problem. That may not be so interesting. We want to know, how does the runtime scale with the size of the problem? And then a quantum computer would be advantageous if the runtime is good relative to a classical algorithm. And also you might ask, what are the resources needed to build the Hamiltonian? How does that scale with the problem size? Okay, so let me just explain again this notion of an oracle, because this allows us to, the oracles allow one to make definite distinctions between what a quantum computer can do and what a classical computer can do. And let me just remind you, if you look at the Shor factoring algorithm, which is an amazing thing, it says you can factor in polynomial time with a quantum computer, but no one can prove that you can't factor in polynomial time on a classical computer. So the Shor factoring algorithm compares the performance of an actual algorithm with the best known classical algorithm. So it's only better relative to what we know how to do. It's not provably better. But in this example I'm going to talk about right now, the Grover problem, which I hope some of you have seen before, but if not, it's fine. We're going to have a provable performance guarantee where the quantum computer outperforms the best classical. So an oracle is an abstract thing where you give it an input and it gives you an output, but with no other information. So for example, in the Grover search problem, it's defined on the integers from 1 to capital N, and the function returns a 1 on all the inputs except for one of them, which I call the winner, W. And on that one, it outputs a -1. Now, suppose that you want to know what's the winner. You want to know what it is, but you're only allowed to query the oracle. So you call the oracle and you say, what's your output on 7? It says 1. What's your output on 99? 1. What's your output on 102? 1. And then you have to keep going either randomly, but of order n times before you find the winner. This is called unstructured search. But amazingly, with the Grover algorithm, if you have a unitary transformation, which I define below, UF on X is f of X, X. So it puts a phase of -1 in front of a computational basis state labeled from 1 to N. Then the Grover algorithm finds the winner in time n to the 1/2 with the n to the 1/2 calls, and this algorithm is best possible. So this is a provable speed up because it's relative to something you just can't beat classically, the capital N. So, and so again, the point here is that even if you have a fast classical algorithm, which is the blue line, it's a fast classical algorithm because it's not taking a lot of time in the beginning. But the quantum algorithm goes like square root of n. There will be an n beyond which the slow quantum computer will, because it's making fewer function calls, will outperform the best, any classical algorithm. So this is called provable algorithmic speedup. So the question when we saw this was, is there like a Hamiltonian version of this? So I worked this out with Sam Gutman, who I went to high school with, and we still collaborate. Anyway, so we said, let's imagine a Hamiltonian oracle problem. So now we have a Hamiltonian, and on the diagonal, it's all ones, but there's one place where it's a -1, but I don't know where that is. And I want to find that out by running a quantum computer. So what we imagine doing is adding to this Hamiltonian a driver, which you can design, which does not, we don't know what W is. This is an artificial world where you're evolving with a Hamiltonian. It has a secret in it, which is where this -1 is. But we're just going to play this little game that you have the access to this Hamiltonian. You want to know where that -1 sits. Well, it turns out that you can add something to this guy, which evolving in time n to the 1/2 will bring the quantum state into one where this marked item is revealed. And also, we can also prove that there's no quantum algorithm that could do this in time less than n to the 1/2. So here we have a Hamiltonian version of a quantum problem, of a classical, excuse me, I misspoke. We have a Hamiltonian version of a discrete unitary gate model computation. And I'm going to focus mostly on these Hamiltonian problems because they're more natural for physicists, I think. So, and one thing that Sam and I thought about is what we call quantum walk in continuous time. And here, what we imagine is you have a graph. A graph is a bunch of vertices with edges. This is a mathematical concept. A graph, it's a bunch of vertices with edges. I gave an example over there. I didn't mean to make it plainer. And you can imagine that you have a quantum system where the Hilbert space dimension is the number of vertices in the graph, and you have a basis for that Hilbert space where each A corresponds to a vertex. So corresponding to each vertex is a Hilbert space vector. And then we're going to define a Hamiltonian, which is basically the adjacency matrix of the graph. So the Hamiltonian will connect two vertices if there's an edge between them. So AHB is -1 if there is an edge between A and B, and it's 0 otherwise. So H is minus the, I don't know why we made it minus the adjacency matrix and not plus, I can't remember. But anyway, H is minus the adjacency matrix of the graph. And then if you evolve with this Hamiltonian, this is the analog of a classical process where you jump around the graph starting in a node. Like you can imagine a classical process where I started a node in the graph and I jump to the adjacent nodes, and then I jump and I jump and I jump. And you could ask questions about where do you end up. But here we're going to do it quantum mechanically. So the evolution is really deterministic because quantum mechanically, your evolution is by the Schrodinger equation. It's completely deterministic until you make a measurement at the end to see where you are. Quantum mechanics is deterministic until you make the measurement. You know, now it's true though that maybe you might think of it as all spread out over the whole graph and some complicated superposition, but it's a deterministic process. Now, oh, why am I not advancing? Okay, there. Now, I'm going to show you, this is a little cute example of how we used the quantum walk to show that we could solve a problem faster than one could solve with a classical computer. And it's going to be an oracle problem because otherwise I couldn't prove it's better because I have to have the oracle to help me. So anyway, I'm going to try to go through this. This is sort of just, I'm doing this because it's sort of fun to see this kind of problem, which involves a game, and yet we have a nice quantum result. So I want to imagine a game, and we have two people playing the game, and it's you go, I go, you go, I go, you go, I go. And there are two ways you can go. You might go left or right, and I go left or right, left or right, left or right. And at the end of M steps, where we come to a final position, and each of those final positions, according to the rules of the game, is a win or a loss for me. So the rules of the game say whether when you look at the final position, whether I win or lose. And you know, so this is a very abstract kind of game because it just says whether the final position is a win or a lose. And there's no hint as you go along. Like if you're playing chess, someone might say, hey, it's a really stupid idea to lose your queen or, you know, put your king in the middle. But here we're only looking at the final position to see whether it's a win or a loss for me. But so if you look at this, if these are final positions or wins or losses for me, and here it's your move, and then, but before that, it was my move. Now, you'll see the top of the tree represents 2 to the m possible histories of the game, and each final position, according to the rules of the game, is a win or a loss for me. But now, in this setup, it's determined at the outset, who's going to win the game if we both play best possible. I'll show you why. Because let's look at the top of the game tree. Every node is a win or a loss for me. So if your move is one below, well, if you're here and you see that whether you go left or right, I win, you lose. And right here, if you see that if you go this way, I win, but if you go this way, I lose, you're going to win because you're going to go to the place where you win. So I can label everything here as a win or a loss for you. But then at my moves, if I can see all the way to the end, I'm obviously going to go to the places where you lose. So here it's a win for me because I can go where you lose. But here it's a lose for me because both these places you win. And then you can recurse down the tree and you see at the very beginning, if we both play best possible, it is determined at the beginning who wins. So this is a very simple abstract game, but it's known who wins. But now you can ask a question. Do I have to look at every single one of these final positions to determine who wins the game? Is that necessary? Well, it turns out you don't have to. You can look at a fraction of them. If there are n final positions, if you only look at n to the 0.753 ... and that comes from the square root of 32 or square root of 33 or something, some crazy number, you can actually come up with a probabilistic strategy, which with 100% probability, after you do enough repetitions, will determine this without examining every single final position. But that's also best possible classically. So now, you see, though, let me relabel these trees and let me think of a W as a 1 and a L as a 0. So this tree I've just relabeled like this, but what's appearing at the bottom of every one of these is the not and of the thing above. Like the and of 1, 1 is 1, so the not and is 0. The not and of 1, 0 is a 0, so the not and of it is a 1. So this tree has a lot of inputs, and then at the very base, you're taking the not and of what's above, the not and of what's above. And so we can call this thing, in the technical term, is called NAND tree, the NAND tree evaluation. And what we showed is a quantum algorithm that solves this. And I should say this was me, Gutman, and my collaborator, Jeffrey Goldstone, who's the same guy as Goldstone bosons. He turned his interest to quantum computing around 20 years ago, but he's 89 years old now and has not been working. But at this time, in 2000, a few years ago, he was a participant in this. But anyway, what we did is we showed that you could, by using scattering theory, that you could attach this structure using the Hamiltonian, using the quantum walk idea, and that you could build an initial packet here, which is right moving. And if that initial packet hits the base, that if it and then you measure on the right, we could show that you would end up on the right if and only if the NAND tree evaluated to a 1, and we would end up, and it would reflect 100% if the NAND tree evaluated to 0. Now, we did this by computing the transmission coefficient as a function of energy by building a packet here and scattering it. Now, but this was really only true at 0 energy. So to get something which was essentially 0 energy, by the uncertainty principle, we had to make it very big because we needed to concentrate the energy at 0. So we had to make it very big. And in fact, we had to make it size n to the 1/2, so that the energy spread was narrow enough that the transmission coefficient here at energy 0 was just right, so that this would work. And it's because this thing had size n to the 1/2 that it took time n to the 1/2 to get through. But in any event, this thing, I won't go into more about it, how we did it, the scattering theory. Anyway, we were able to prove that the transmission coefficient at energy 0 was the NAND. And I should say that this thing, although so this was a provable speed up over the best classical algorithm for NAND tree evaluation. And it was immediately turned into the conventional quantum query model, because although we did it by continuous time evolution using scattering theory, the computer scientists jumped on it and turned it into a conventional query model algorithm immediately, and they could evaluate all kinds of other Boolean formulas. And the other thing we could prove, which I won't get into because I don't have that much time, is that n to the 1/2 is best possible. We could prove that no quantum algorithm could beat n to the 1/2. So we got n to the 1/2 and we proved it was best possible, and it beat the best classical algorithm for the problem. But it was based on scattering theory, which is why I always like this example, because it took ideas from physics, and I told you the topic was physics-based. So I better not spend too much time on this, but I want to give you another physics-based approach, which is called quantum computation by adiabatic evolution. And this is me, Goldstone, again, Gutman, and Michael Sipser, who's a computer scientist. He wrote a textbook on complexity theory. And basically what happened is, you see, I was talking to Goldstone and Gutman about quantum computing, but we didn't really know what we didn't know what a conventional computer did at an abstract level, but there's a whole science, the whole mathematical field of computer science where they talk about the power of computers. And we had to learn that. And so we decided we would get help, and we enlisted Michael Sipser, who joined our effort, and he really shifted our focus more to conventional computer science, which we knew very little about, but we kind of learned it. Anyway, so the team at that point was included Michael Sipser, and this is a general approach to combinatorial search, and it's universal, and it's possibly a good design for building a quantum computer. Let me tell you what the idea here is. Suppose you have a time-dependent Hamiltonian, and you look at, and I'm going to plot here the eigenvalues of the Hamiltonian as a function of time. So this is the ground state. Can people see my pointer? Is it clear there or no? You can, great. So this is the ground state, the first, and you never have level crossings in quantum systems unless you have symmetries, and they're very special. So you can just so you never see a diagram in which levels actually cross. They're always repelled by a little bit, unless you have a symmetry. So this is a very generic picture of the levels of a quantum system. And the lowest one is the ground state and of the system at each time t. And so the instantaneous ground state is the quantum state, which is the lowest energy at each time. That's called the instantaneous ground state. Now, suppose though, I evolve with the Schrodinger equation, but at time 0, I'm in the ground state of the instantaneous ground state, which is the ground state of the Hamiltonian. Now what happens is you evolve slowly in time. And the adiabatic theorem says that if you go very slowly, the evolving state, the actual quantum state of the system, will be the instantaneous ground state. You can kind of think of it like this. Suppose you put like a penny or something in your hand, like a piece of thing, and I slowly move my hand. Well, as I move it, the pen stays in my hand. It stays in the local minimum, even though I'm moving it. But if I jerk my hand quickly, the pen falls out. So that's quantum mechanically true as well. If you change a quantum system very slowly and you start in the ground state, you'll stay in the ground state of the evolving system. So that gave us an idea for looking at a combinatorial search problem. So let me tell you what, for looking for how to solve a combinatorial search problem. And I'm going to say this again later in another context, but combinatorial search problems are the following thing. You have n bits, and here the bits are valued 0 and 1. And then you have clauses. What a clause is a little truth table acting on a subset of the bits. So it might say, like, I give you an example here. The clause might involve bits 7, 99, and 103. And it says it's true if and only if the sum of those 3 bits is a 1. Then it's true, it's satisfied. Or another very conventional thing is to say you have a clause involving 2 bits and it's satisfied if they disagree. Like or maybe you want to say they're satisfied if they agree. Whatever it is, I have restrictions on the subset of the bits with little truth tables associated with those subsets. And the mother of all computational problems is, can you find an assignment of the bit that minimizes the number of violated clauses? Now, what we mean by this is, well, you can always do that if you search through all 2 to the n possible values of the bits. So there's an exponential algorithm, search through every assignment to the bits and find the bit assignment that violates the fewest number of clauses. And but that problem, it is generally believed that there is no polynomial time algorithm that can solve this problem in worst case. And this is the belief in computer science language that P does not equal NP. It's not proven that P does not equal NP, but it is very universally believed that for this particular problem, there's no polynomial time algorithm that can solve this problem for worst case, meaning, for any set of clauses. And it's considered intractable on a conventional computer. But there's sort of something we can do in the quantum domain that we can imagine. And so let's imagine we build a cost function, E, of bit strings, which counts the number of violated clauses. So I give you a string, and now I have a cost function, an energy, which counts the number of violated clauses. Now, if you know the global minimum of E, you can solve the combinatorial search problem. Now, this is a very easy problem to describe. If I give you the clauses, I can even give you a little computer program that will evaluate the cost function. But what's very hard to do is to know what the real minimum of it is, because there are 2 to the n, which is an exponential number in the number of bits. Imagine n is like 1,000. then just 1,000 is not that big a problem. 1,000-bit problem is not that big, but 2 to the 1,000, I mean, you don't even see numbers like that in cosmology. 2 to the 1,000, it's beyond cosmologically big to the search space of just 1,000 bits. But and here we're talking about worst case, meaning, you know, I'm really going to try to fool you by putting the minimum someplace where you have no idea where it is. But now, so this cost function is easy to describe, but hard to minimize. So the idea of the quantum approach is to first encode that cost function in a quantum Hamiltonian, where it's diagonal in the computational basis. So I encode the cost function as part of a quantum Hamiltonian. Now the goal is to find the ground state of HP, because if I know the ground state of it, then I have solved my problem. So now what we're going to do is construct an H of t with H of 0, some easy to construct Hamiltonian with an easy to construct ground state, and where H of capital T is the problem Hamiltonian. And then what we, and I'll give you an example. Like, for example, a standard example is to choose for the beginning Hamiltonian, let's say a magnetic field in some direction. And then I can easily line up my spins in that direction. So I know the ground state. Now what I'm going to do is turn off that magnetic field and turn on the problem Hamiltonian. So I'm going to interpolate between the initial state of the initial Hamiltonian, which has a ground state that's easy to construct, and a Hamiltonian which encodes the solution to my problem. And I'm going to do this if by just following the Schrodinger equation. If I go infinitely slowly, then at the end of the evolution, I will psi of t will be very close to the ground state of HP if the time is big enough. So this is the idea of quantum adiabatic evolution algorithms, where you encode the information in a Hamiltonian, start with an easy Hamiltonian, morph it into the other one, drag the state along, and if you go very, very slowly, it's going to work. But of course, the problem is, and here's a very simple way to do this, an adiabatic design for classical, here, like you might, this is a parameterized Hamiltonian where the parameter just goes from 0 to 1. So imagine I have a parameterized Hamiltonian where it goes like 1 minus SHB plus SHP. So this is the beginning Hamiltonian whose ground state I know. As S varies, I go from this one to HP. But now what I do is I let S be little t over big T. So I'm going to slowly change the Hamiltonian because big T is a big number. And so I'm going to slowly change the Hamiltonian by having it depend on this ratio, little t over big T. And then if I follow this, with just this linear interpolation, I will end up where I want to be. And the runtime, though, is determined by the minimum gap. And the minimum gap is the minimum energy difference between the ground state and the first excited state. And it turns out that you can prove that the requisite runtime goes like 1 over the gap squared. So now, don't forget, these are systems with an exponential number of levels. So you could expect the gap to be exponentially small. So the question becomes, is the gap at the bottom of the spectrum big enough that you don't require exponential time? And therefore, we've connected a computational problem to a physics problem, which is has something to do with the gap. Oh, maybe I'll tell you a little story. I once went to Alexei Kitaev, who's a very famous guy in quantum computing, and he's a big shot in condensed matter physics. And I said, Alexei, if I'm going to give you a certain condensed matter system and I'm going to put on a magnetic field, and I want you to tell me, do you think the gap at the bottom of the spectrum is exponentially small or polynomial small? What do you think it is? And he said, it's going to be exponentially small. I said, why? And he said, otherwise your algorithm would work. So that's the standard, that's what he said, So the standard view from the big shots is, well, since the algorithm can't work, the gap has to be exponentially small. And that's fine. I mean, I enjoy the challenge, but we have not succeeded in proving for a really interesting case that the gap is big. But my talk's about the relationship between physics and quantum computing. And anyway, this is a nice connection. And it's also a nice way to think about designing a quantum computer, because you might design a quantum computer where you always live in the ground state. And that's what the D-Wave machine does. If you've ever heard of the D-Wave machine, it's built attempting to, it runs the adiabatic algorithm. They call it annealing, because the difference between adiabatic and annealing is sometimes with annealing, they're thinking about having a non-zero temperature and maybe getting a little help from trying to just cool into the ground state thermally. But the way I'm describing it is purely quantum. But you might combine the two. And anyway, the D-Wave machine is the physical realization of this. And anyway, I think it's interesting. And I could go on much, much more about this because there's been a lot of work on this over the years, but just doing a quick survey of some of the ideas. Okay, so if this approach works, quantum computers will have power beyond factoring in game trees, of general interest in all areas of computation. And so I say we need to study the performance of the quantum adiabatic algorithm in specific cases. But if this approach works, meaning if we can find an interesting computational problem where we can show the gap is polynomial. Because if it's polynomial, the runtime is polynomial, and that's success. But we haven't done that. So, but I still think it's worth studying. But now I'm going to change topics, and I'm going to talk about a different algorithm, which called the quantum approximate optimization algorithm. And this is me, Goldstein, and Gutman, 2014. And now this algorithm is similar to the adiabatic, but different. I'll show you why. But let me just make a few points about it. One is its general purpose. So it's designed for general purpose optimization problems. Again, there are many interesting problems in quantum computing that have nothing to do with optimization, like simulating physical systems or quantum chemistry. But I'm really trying to think of a quantum computer as something that is being used to solve sort of conventional computer science problems related to optimization or the traveling salesman problem, things like that. I'm not using it for quantum simulation. And maybe quantum simulation is really the killer app of quantum computers because it's very natural. That's certainly what Feynman thought. But I'm looking in a different domain today. But the reason that this quantum approximate optimization algorithm was interesting is because it's general purpose, and we could also prove worst case performance guarantees. So this thing is going to turn out to be much more mathematically tractable than the adiabatic. It also has something called quantum supremacy. If you read in 2019, Google announced that their quantum computer could do something a classical computer couldn't do. And that was called supremacy. But we can actually prove that the shallowest depth version of the quantum approximate optimization algorithm can be used to show quantum supremacy. So that means that it's not a classical thing. And there are other interesting things about it, which maybe I'll get to or I won't. Which we've studied more recently. One is called landscape independence, and the other is looking at typical instances of combinatorial optimization problems. But let me keep going. So let me go back. I know I've talked about it, but I'm going to say it again. But here I've switched my language just a little bit from my bits I'm calling Z's. That's really because the conventional, in quantum computing, the convention is to make the Z basis the computational basis. That's just very standard in quantum computing. I probably shouldn't have used X's on the previous thing, but now I want to make up for that and just insist on using Z's because those are the conventional basis for a quantum computer. So now, again, I have a bit string of length n. I have clauses. A clause is a restriction on the subset of the bits, and it can be satisfied or not. So each clause looks at, let's say, bits 1, 3, and 19, and according to the 8 assignments, we'll make it 1 or 0 for each of those 8 assignments. And now, you see, in the adiabatic, I really wanted to go downhill. I wanted to find the ground state, but for certain technical reasons, here I want to go up. And I could explain why that is. Well, maybe the next formula will really show it. You see, I want to maximize the number of satisfied clauses. I'm sorry for this little switch, but here I want to maximize the number of satisfied clauses. Now, the actual maximum is I call C max, but I don't know what it is, but the C max is this. And then the approximation ratio is the value I have divided by the maximum. So if I give you a string, I can tell you how many clauses does it satisfy. I want to divide that by the maximum number, and I want to make that big. And you can kind of see why I need to go uphill, because if I was going, I want to divide by the maximum number of satisfied clauses. Otherwise, I would have a 0 in the denominator. So anyway, this thing is called the approximation ratio. And so now I'm not looking for the best, I'm just looking for good. I'm looking for a string that does a good job in getting a high number of satisfied clauses. So now I'm going to show you the algorithm. There are 2 ingredients in the algorithm. One is a unitary operator that depends on the cost function, which I write as e to the minus I gamma c, where, so the cost function is a sum of terms which are diagonal in the computational basis, and they commute because they're diagonal in the computational basis. So this is actually a product over all clauses of e to the minus I gamma c alpha. So what this says is, when it hits a state, I rotate it, the phase of each component of the state, by this amount. The other operator I'm going to take is the sum of the sigma x's. Xj is conventionally called sigma xj. And so this is just a magnetic field in the x direction. And now I'm going to define u b beta as e to the minus I beta b, and that could be written as e to the minus I beta xj. So what this does is it rotates the spins by an amount beta around the x direction. And that's why the x direction is not the z direction. The z direction is the computational basis, but these rotations are around the x direction. And then I'm going to start in, oh, wait a second. I'm going to start in a state which is the uniform superposition of all possible strings. So when I'm going to start the quantum algorithm is in this state which it's got a little bit of everybody in it. It's got 1 over square root of 2 to the n of every possible configuration. And all of these little ingredients are actually easy to construct. So then what we're going to do is we're going to alternately apply these operators by P, within P levels. So first I'm going to apply the operator that phase rotates by gamma 1. Then I'm going to actually rotate about the x direction by beta 1. Then I'm going to phase rotate by gamma 2. And I'm going to do this P times. Now, so the circuit depth here is essentially P, because these are all local operators. So what we're doing is we're applying 2P local operators to our quantum state. And it's very important to count the number of things you do, because when you run a quantum computer, this is now, oh, I should say I'm back in the gate model. I'm now back to the gate model. I've left the Hamiltonian model. I'm back in the gate model. So now I want to count the number of applications of my unitaries to see to understand the whether my algorithm is efficient or not. But the point that I want to make is that what my goal now is to create a quantum state where the expected value of the cost function is big. So I want to pick parameters, build a quantum state, and then I want to engineer it so the expected value of the cost function is big. And for any set of parameters, there's a maximum at depth P, which is overall parameters I can just maximize. But you'll notice that as I increase the depth, I can only do better. The reason for that is because if I think of the algorithm at level P, it's really the same, or let's say at level P minus 1, that's the same as the algorithm at level P with the last two parameters set to 0. So every time I add a layer, I can only do a little better. So the performance can only increase. And we can actually prove that if you have an infinite number of steps, you can actually achieve the maximum. But I'm not interested in an infinite number of steps. But what you can do is you could imagine running the algorithm in this way. And this is very common now in the world of quantum computing, where people talk about variational quantum algorithms. And this is an example of one. That's you start with a given set of angles, parameters for your quantum computer. You build a quantum state. So you use the quantum computer to make the state. And then you measure a string and you evaluate the cost function. Now, you can then do that again with the same angles and try to estimate the expected value of the cost function. But then what you're going to do is try to change the angles in some way to go uphill. So this is called a variational quantum algorithm, where you set your parameters, you get an answer, then you try to change the parameters and you go up. Then you change the parameters, you go up. If you go down, you don't accept those parameters. So this is called variational quantum algorithms. And it's sort of an obvious way to run the algorithm. But it turns out, if at the shallowest depth, we can actually analyze the performance of the algorithm by hand. So I don't need a quantum computer to know how well the algorithm is going to do. I can actually mathematically analyze it. I don't have time to show you, so I'll just show you there are some slides with a lot of equations. And in the end of the day, what we could show is that for a particular problem called max cut, there's a particular computational problem. Maybe I should even say what it is. Oh, maybe I won't. I don't have time. It doesn't matter. It's just a math problem. There's a little math problem called max cut. And what we could prove is that the QAOA will produce a cut that is at least 0.6924 times the optimal cut. So what that means is that we now, which we couldn't do in the adiabatic case, is we have a worst case performance guarantee. I can prove that the QAOA will do this well. Now, that's very nice, but that doesn't beat the best classical algorithm. There's a better classical algorithm for this problem. It's called the Gomans-Williamson algorithm. Gomans is a professor at MIT in the math department, and there's a very famous algorithm for max cut that gets 0.87. And we are not getting that at the shallowest depth, but we are doing better than what you would get if you random guess. But now I want to tell a little story. We then looked at another problem, which is called E3-Lin2. And I'll tell you what this problem is. We have n variables and m equations. And each variable, here the z's are 0 or 1. And every equation says that I want zi plus zj plus zk mod 2 to be 1 or 0. So the way you specify the problem is I give you a list of triples, and I tell you whether they add to 1 or 0. So basically, I'm giving you constraints because I'm telling you I'm happy if the bit values obey this equation, and I'm sad if they don't. So the task is to find the string that maximizes the number of satisfied equations. So we have more equations, many more equations and variables, and the goal is to satisfy as many equations as you can. You can't satisfy them all. And this is a very hard problem computationally for certain reasons. And it turns out that one algorithm for this is guess a random string. So you just guess a random string, then you satisfy half the equations. But it turns out that this problem is so hard that if you could guarantee that your algorithm will always give you an approximation ratio of a half plus epsilon for any epsilon, that would imply P equals NP. So that's like, this is a very tough problem from a computational point of view. There's a way to make it a little easier, and that is to tell you that every variable is in no more than the equations. And if you do that, you get a little help because you know something about the problem. And in the year 2000, there was a classical algorithm that went like a half plus constant over D, but then our quantum algorithm got a half plus constant over D to the 3/2, which beat this. So then for a very brief period of time, we had a quantum algorithm that beat the best classical algorithm for a computational problem. But then Scott Aronson blogged about it and said, oh my God, there's this great new quantum algorithm, it beats the best classical. So that got the computer scientists all riled up. And they got together, and 10 of them got together. This is a very high-level list of computer scientists, but these 10 guys got together and they beat us. So they got this one. We did this in 2014. In 2015, this international conspiracy got us and beat us and got that. And now I'm not going to go into more of the details of this, but anyway, I think this is a really nice example where, the quantum algorithm, we stimulated the classical algorithm to do better than us. And there are many still interesting math problems associated with this QAOA. It's called the QAOA, which I just say one more thing because I have, but like one problem we looked at is the Sherrington-Kirkpatrick model. We analyzed the performance of the QAOA on this model. This is the reason I bring this up is because, let me just tell you what this model is. I know I'll stop in 2-3 minutes. If you look, the Sherrington-Kirkpatrick model is the following model. I have n bits and I have bits which have value plus or minus 1. My cost function is 1 over square root of n, the sum over a less than b, j, a, b, z, a, z, b, where the j, a, b are randomly chosen to have mean 0 and variance 1. So they might be plus or minus 1 variables, they may be Gaussian. This thing is called the Sherrington-Kirkpatrick model. And the energy density of this model was computed by Parisi, who won the Nobel Prize for it last year, for this calculation, okay, for showing that as n goes to infinity for typical instances, the maximum divided by n is 0.763. So this is a really interesting problem with a long and really fascinating history in condensed matter physics. So we attacked it with the QAOA, and I don't have time to show you all this, but at the lowest level, we get 0.303 as compared to 0.763. And if you look at our numbers, as we increase the depth, we get better and better. And we're trying to see whether, we want to show that for n goes to infinity and then p goes to infinity, we achieve the Parisi value. That's one of the things I'm working hard on now. So this is, again, I'm trying to tell you about physics and computer science. We're trying to use a quantum algorithm to analyze an interesting problem in physics. So we want to then apply our techniques to other problems where instances are drawn from a distribution. And I think that's the end of my talk. But I'm sorry I rushed a little bit, but there's so many interesting relations between physics and quantum computing. I just wanted to give you a feeling for that. Okay, thank you.
Thank you very much. That was very exciting and pleasure indeed.
Thank you. I'm happy to answer questions.
Yeah.
I'm not in a rush.
Questions, please.
I see a hand up.
Yeah, okay. Thank you very much for the very exciting talks. It was a very nice overview of the algorithms and comparison of the gate-based and annular examples. So I have a question about the gap that you mentioned in the first half, I should say. So you mentioned that it can be polynomial depending on, I think, certain symmetries, right? Is that a Hamiltonian specific condition, or is this just a physical implementation dependent case?
No, wait a second. No, the gap at the bottom, I mean, there are problems where I can construct something where the gap at the bottom is polynomial, but they're not computationally interesting. What I want to do is find a problem where, I mean, there are problems in the line where spin models in the line where the gap goes like 1 over a number to the square root of n, but those are due to Daniel Fisher. But I mean, we have never succeeded in finding a situation which was computationally interesting where we could show the gap was big. But I'm really sorry, but what was I'm not sure I answered your question. I don't think I did.
I was trying to understand if the gap is just a if the behavior of the gap, whether it is polynomial or exponential or any other, depends on the problem type, or it depends on the implementation through the physical system, or
well, no, in my case, I am imagining that I have that the math I do is independent of the physical system, because we're imagining that I'm actually building that Hamiltonian in the lab and I am implementing it, and I don't care how you do it. So the things that I look at do not depend on the implementation that's at a higher level. It's just saying, you know, I write down the thing on a piece of paper and I say, what's the gap? And then the experimentalist has to make it happen. Yeah, so I mean, the gap could certainly, I'm sure, the physical system, and also it's possible that, you know, another thing that you can do is this. I mean, it may be that you have a very tiny gap, but there may be a route around it by taking a different path in Hamiltonian space, and your implementation may do that.
This actually guides me to the second question. So I actually use the D-Wave quantum annealer, and they have a sampler which actually discretizes the number of time steps in the annealing of the Hamiltonian. So in this case, they basically specify the number of annealing steps or the samples that we pick up to minimize the states that minimize the total energy. But the problem is we never reach a provably minimum energy state. We always try to approximate it. So is there any route for proving or for specific questions or problems or at least some Hamiltonian cases for the annular, for instance, where it can reach the minimum state with some specific sampling conditions?
Well, okay, let me say a couple of things. Well, first of all, I haven't actually followed lately the details of the D-Wave's performance. I mean, I probably should, but I haven't. But, you know, very often you don't need to find the best state. Very often an approximate solution will suffice. So that's why I was switched when I talked about, I didn't have enough time, but, you know, when you talk about the problems like max cut, the Gomans-Williamson does not find the best cut. It finds something that's within 0.87 of the best cut. And so very often finding a good solution suffices. Now, it depends on your question. Like, you may not know. I mean, I think in general, finding good solutions would be very valuable, but it depends. But if you want to prove it, it's very challenging sometimes to be able to prove that you found a solution that is within some fraction of the best. That's very tough to do. So if you run the D-Wave machine, you know, what they do, I believe, is they look at their solutions and they compare to what the classical solvers do. And then sometimes I think they claim that they're doing very well relative to the classical solvers without proof.
That's the case, right?
Yeah, that's the case, right? But I think that's okay. You know, I mean, that's fine. You know, you do what you can do. Proof is very evasive. It's very hard to prove things. And in the history of traditional computer science is filled with things that were developed heuristically, where people didn't really know why they worked. And then when they worked really well, better than they expected, and then much, much later, it was proven why. It really depends on who you talk to, whether you care about proof. If you talk about people who write textbooks on complexity theory, they don't care about, you know, heuristics. They only care about provable worst case performance guarantees. If you talk to a company that is an airline trying to, you know, route its planes, they may care about having a good solution. You make a one, you know, I have a friend, his brother made a 1% improvement on some oil refinery problem as an engineer, and, you know, they were very happy. They gave him a very big bonus. So it really, you know, depends on who you talk to, what your problems are.
So I have one last question. So in the gate-based model that you cascaded the operators one after another in the variational quantum algorithm. So does the coherence time change anything regarding the number of gates that we can use? Because at the end of the day, we have to restrict the number of gates that we can apply.
Yes, great question. You see, okay, so people have been running the QAOA on hardware. The QAOA is the quantum approximate optimization algorithm. People run it on hardware. And the thing that's very attractive about it is that you can, even at the shallowest depth, have worst case performance guarantees. So that's really nice. But if you, and now it can, the performance theoretically can only improve as you increase the depth, because as you make it deeper, you have a bigger search space, you can only do better. But if you look at the experiments, what happens is as you increase the depth, like from 1 to 2 to 3 to 4 to 5, it starts to go down after 3. And that's because the decoherence in the device kills the performance which you have theoretically established. And this is seen both in, let's say, hardware implementation by IonQ, who ran this, and they saw the performance go up and down. Google saw it go up and down. So yes, I mean, you know, your coherence limited. Then that's why it's good to have a shallow depth algorithm, because the fewer gates you apply, the less the cumulative effect of error.
Mm-hmm.
Does that help your question?
Yeah, absolutely. Thank you very much. Very instructive help. Thank you.
Yeah, my pleasure. More questions?
In chat, we have some questions. Can you read?
You want me to go to the chat? Okay, let me see if I can figure out how to do this. I guess I'm going to stop the share.
Yeah.
And then I'll go to the chat. Is that okay? Yeah.
Yeah, sure.
Oh, okay. For the first part, do we omit some steps on the entry where we do not care player two's move? Yeah, that's right. In other words, yes. You see, if you analyze the, there are cases if you, the quantum algorithm doesn't do what you're saying. Oh, I should read the question. For the first part, do we omit some steps on NAND tree where we do not care player two's move? Some branches are always one, whether right or left. Yes, that's actually what the classical algorithm does that. What the classical algorithm does is it randomly samples possible routes through the tree, and it cuts things out where it no longer matters. Like if you come to a point where early on, where you know that whatever you do, you lose, there's no point in exploring the rest of the tree. So the classical algorithm does that probabilistically, and that's how they get n to the 0.7, whatever it was. But still, it was proven that you can't beat that. I think it was Avi Vidgerson proved that strategy classically cannot be improved. But this is worst case. This is for the worst case assignment. But your question is right. But the quantum thing doesn't look at all like that. It's somehow another, I don't know what it does, but it certainly is not selectively pruning the tree. It's just sort of doing its thing. So now let me read the next question. Second question, for the approximate optimization, does the algorithm transform the problem into a decision problem by using quantum oracle? No, because no, I'm not. The QAOA so far, we have not looked at it in the oracle model. We've been looking at actual problems where, like max cut, where I give you a graph and I tell it to you, and then you can ask questions about the graph. There are no, to date, oracle results on the QAOA, but I have to tell you, I'll confess, I am working on that with my collaborator, Sam. In fact, he called me yesterday to talk about this, but I don't have an oracle result on the QAOA. So I don't have a proof, I don't. So again, all we can do on the QAOA is compare to best classical. Does that answer your question, whoever asked it? Okay, I think it was Uger. Okay, and then the next question, what is the importance of controlling of quantum adiabatic processes in applied physics? The gap first excitation state and ground state is small and eigenvectors are near around each other. What can we do with this in applied? Well, I don't really know. The question has to do with, I guess, the application of the algorithm in a physical setup. And can you somehow or another take advantage of the hardware to somehow or another try to stay in the ground state? I don't really know the answer to that. I mean, again, I'm sorry, but I just work on it in a very mathy way. And I cannot answer that intelligently about the effect of the hardware on the gap. Okay, now there's a question in Turkish, which I cannot answer because I don't read Turkish, although my grandparents did. Okay. And then, then it says you cannot start your video because the host has stopped it. Okay.
More questions, please. More questions.
Please, I'm happy to talk. Any question?
Any more question? Yes. Oh, okay. It seems that there are no more questions.
Okay.
So, if you don't mind, Edir, we can stop here.
Sure.
Thank you so much for this talk. That was a pleasure and honor. I also hope that we will meet in person in nearest future. So you're welcome always.
Thank you. I would really love to come and visit you guys and girls.
So thank you. Bye.
Bye.